Now we're going to derive the differential equation for conservation of mass. In order to do that, we're going to consider an infinitesimal packet of fluid here, small region of space actually that contains fluid. Delta z, delta x, and delta y are its dimensions, so it's a little parallelepiped, a little box that has those three dimensions. The difference between this and control volume analysis that we did in the past is that we're going to take the limit as delta x, delta y, delta z go to 0 to get a differential equation. So it's not going to remain a large box. It's going to represent an infinitesimal point in space. The mass conservation equation, fundamentally, you're familiar with it. If you want to ask how much mass is in this box and how that mass is changing in time, you have to consider the rate at which mass is entering the box and the rate at which mass is leaving the box. And that obviously is going to lead to either an increase, a decrease, or no change in the amount of mass in the box. The amount of mass in the box can be represented by the density times the box's volume. So we have delta x, delta y, delta z is the volume of that little tiny box. And of course, the density there is rho. We plug that into our equation. So we have d by dt of rho, delta x, delta y, and delta z. You guys, I think, are all taking EGR 301 now, so hopefully you've seen partial differential equations. You certainly have seen partial derivatives in Calc 3. So we're taking the partial derivative because, of course, the mass could change in time, but it also could change in space. We're not worried about space right this second. We're focusing on one region of space, but that's why it's a partial derivative. Of course, the sum still of all the possible inflows and minus the sum of all the possible outflows. We're going to assume for the moment that delta x, delta y, and delta z are constant. So as I say, we'll take them infinitesimal at some point, but for this derivation, we can say, oh no, we're studying this particular little box of fluid, so we can pull those guys out in front. Delta x, delta y, and delta z are not going to change with time. So we have d rho dt is equal to the sum of the inflowing mass minus the sum of the outflowing mass. All right, now it starts to get more complicated and you're going to have to pay a bit more attention. So we're going to go ahead and represent this with our, do it like this so you can see the box still. So we're going to try to represent this inflow and outflowing mass, that's in minus out, using rho and u and the things that we, the variables of fluid mechanics. So if you want to know how much mass is going in the x direction, you would say, well, there's this box here. This box here is facing in the x direction. So if there were velocity going out of this box, it would be carrying mass out. And if there were mass going in, velocity going negative x, it would carry mass in. So there's going to be a term here, minus u rho evaluated at x plus delta x. So that's representing this surface. And that's going to carry mass either in or out, depending on u. If u is positive, it's going to carry mass out, hence the negative sign. And if u is negative, it's going to carry mass back in. It's going to do that over the area of that surface, and that surface area is delta y, delta z. So that's that term. On the other side, we have the same thing, but it's evaluated at x, and if it's positive coming from the back, then that's going to carry mass in, and if it's negative, it's going to carry mass out. So it has the opposite sign. But these are evaluated at x and position x and x plus delta x. So this position is x, and this is obviously x plus delta x here. Okay? So now we're going to do that same thing for the other sixth side. So that's side 1 and 2, both facing the x direction. We're going to have exactly the same thing in the y direction and in the z direction. So in the y direction, you have a v velocity that's coming up from the bottom potentially. So there could be mass coming from the bottom of the box, and if the v is positive, it'll bring mass in. And then if it's at the top of the box that we can see here, if it's positive, it will carry mass away from the box. And the areas of those surfaces are delta x and delta z. Delta x times delta z gives you the area of those little box faces. And finally, of course, you have the same exact thing in the z direction. So the z direction, if it's coming from this side, that would be a positive W would bring mass into the box, evaluated at z, and a negative W would bring mass into the box if you were at z plus delta z surface. And those surface areas are delta x times delta y. So that is our analysis of mass in and mass out through each of the 6 surfaces of our box. We're now going to plug that into our differential equation that we're developing. So on the left-hand side, we had delta x, delta y, delta z times d rho dt. And that was all equal to mass in minus mass out, which is all of this stuff. So I have delta y, delta z times u rho at x minus u rho at x plus delta x. Then I have delta x delta z times v rho at y minus v rho at y plus delta y. And finally, I have delta x delta y times w rho at z minus w rho at z plus delta z. So I've got my total mass change on the left is equal to the mass being brought in or out of each of the 6 faces of the box. Now I can divide everything by delta x, delta y, delta z. So when I do that, I'll write it here first. It's d rho dt on the left. That's pretty easy. This term has delta y and delta z in it. So the only thing that's going to end up being in the denominator is delta x. So I have u rho at x minus u rho at x plus delta x over delta x. This term has delta x and delta z in it, but not delta y. So the only thing in the denominator is going to be delta y. V rho at y minus v rho at y plus delta y divided by delta y. And the third term has delta x and delta y, but doesn't have delta z in it, so the denominator has only delta z. Z minus w rho z plus delta z, all divided by delta z. All right, hopefully that's triggered a memory for you. These guys right here look an awful lot like derivatives. So in the limit, if you recall from your Calc 1 days, way back in Calc 1 when you were little bitty babies, there was a formula that the definition of the derivative, df dx, was equal to f at x plus delta x minus f of x divided by delta x in the limit as delta x goes to 0. So that's what we have here. We have 3 different times. The function here is u rho. It's u rho at x plus delta x, u rho at x. The negative sign is switched, as you can see compared to this. That's going to be a negative derivative, but that's fine. It's going to be negative derivative with respect to x of u rho, negative with respect to y, derivative of v rho, and negative derivative with respect to z of w rho. So the final equation in the limit of delta x, delta y, delta z goes to 0 is d rho dt is equal to negative d by dx of u rho, negative d by dy v rho, negative d by dz w rho. Usually this equation is written so that everything is on the left-hand side. So we will do that. D rho dt plus d u rho dx plus d v rho dy plus d w rho dz is all equal to 0. That is the conservation of mass equation for fluid mechanics. That's the real one. And this one is applicable to all systems. We haven't made any assumptions yet. So there are no assumptions in this. Density is not constant, obviously. There's d rho dt out here. So this is completely valid. It's saying, change in density with respect to time, related to the change in u rho, v rho, and w rho with respect to space.